Let's get started. I'm very pleased today for this speech to be welcoming Viton Vitanis. Viton is the head of risk analytics at Viseca Card Services, which is one of the biggest card providers in Switzerland. His team develops tools and methods aimed at preventing fraud, for instance, but also assessing credit risk scoring and things like that. He has a PhD in biomedical engineering from the ETH in Zurich, and today his speech will be about how at Viseca they have been exploring various approaches regarding machine learning for fraud prevention. And also Viton will describe us the use of machine learning to score card not present transaction, a new approach to interpret the individual scores. Thank you, Viton.
Thank you very much.
Please join me in welcoming Viton.
Thanks. In the next 30 to 35 minutes, I will try to present to you a rather difficult to identify fraud case we had approximately a year ago at Viseca Card Services, and then I'll try to show you how interpretability can help us make better decisions when judging whether a score delivered by a fraud model makes sense or not. But before going into that, I would like to show you some interesting numbers. When it comes to cybercrime in general, not only payment fraud, but cybercrime in general, we're talking about a huge business. We're talking about a problem of the order of $350 billion. The average cost of a data breach is approximately $4 million. These are numbers from this year. And the average record size of a data breach is 25,000 records. Huge numbers. What is more disturbing, actually, is this last number. So the average breach life cycle in days in 2019 was 279 days. What does this mean? This means that from the point we have a data breach until to the point that this data breach is being brought into attention or is being published as an event, we have 279 days. Plenty of time for the fraudsters to export the data outside of the network that has been breached, share the data, sell the data, maybe in the darknet, and plenty of time to commit fraud. Breach Level Index reports another number for 2018. They say that the number of records lost or stolen during that year, on average per day, is 6 million records. To use an analogy, from now until the end of this presentation, the number of records lost or stolen during these 30 minutes is almost equal to the number of inhabitants of Lausanne. This is a very, very large number. And when it comes to the industries, right, you see that the financial industry, despite the fact that it's rather careful when it comes to protecting data, it is still affected by 14% of all data breach incidents. Last number that has to do with financials. It's a rare case that you have a published number with respect to payment fraud. The European Central Bank last year presented some numbers about 2016, and you see here that fraud with cards issued within the euro area amounted to $1.8 billion. But there is another dimension to it. So it's not only the financial impact of fraud, but it's also the societal impact. As you see here, there is this study in a book that was published last year that states that 20% of the cyber criminals reinvest the money they earn from cybercrime in further criminal activities. Of course, they buy equipment, they buy more crimeware to commit more fraud, but they also participate in the production of illegal drugs, human trafficking, and they even finance terrorism. So it's not only the financial impact that we see in our companies, it's also the societal impact that we rarely talk about. This makes our job, of course, very interesting, but our successes and failures very critical. And this brings me to the topic of this presentation, which is credit card fraud prevention. We had an excellent presentation before. I will try to give a small introduction how a credit card transaction takes place, so that we have the common base, and then go into the details of our fraud model. So in Switzerland, we have the so-called four-party system. We have the cardholder that presents the credit card at the merchant in exchange for goods. And then the merchant, the first thing the merchant does is sends an authorization request to their own bank, the acquiring institution, which then forwards this authorization request for this specific card, for this specific amount, to the issuing institution. This is us, Viseca, for example. In this case, what we do is we perform an authorization check. We check the validity of the card, if there is enough limit on this card, and we do this part here, very critical fraud control, and this has to take place within milliseconds. Because once there is an answer, approval or rejection, we cannot retract it. The money has left the account of the issuer, in most cases. Now, how do we prevent fraud in such a setting? The very typical use case is the one that was described in the previous presentation as well. We have a risk engine containing several hundreds of rules, usually, that takes authorizations in real time and makes a decision, approval, or decline within these few milliseconds. This is an example of a rule that I made up. I think it's not very far from the rules that we use at Viseca. So let's assume we have a card that performs a transaction now, and we say if this is the first transaction of this card at the merchant, and the average temporal distance between two transactions at the merchant, or this specific merchant, is larger than 10 minutes, and the last transaction at this merchant was a few seconds ago, and the amount is above 50 Swiss francs, then decline the authorization. If you're lost, I'm lost as well. So this is a complex, rather complex rule. Tries to show a pattern in order to prevent fraud that happens according to this if-then case. What we usually do at Viseca is we try to bring rules that belong together in the so-called rule blocks. So here, the number of rows, in the rows we have the rules, and in the columns we have the different features, let's say, or variables or aggregates that we take into consideration when we want to judge a transaction. And then we have several rule blocks together that are being used to judge a certain fraud type, card present, ATM, e-commerce, and so on and so forth. Here, I prepared an example for you. I was motivated by real use case, but as I clearly state here, the dates, times, merchant names, amounts, countries have been modified. Should I repeat? Okay. Now, we have a customer that has done a lot of travel transactions in the past. So you see, this customer has been in Seoul, in Athens, Paris, Moscow. They rented a car in the US. They booked a flight with British Airways. They used a travel portal, then EasyJet, then another hotel in Greece. And we know that between the 21st of June and the 17th of April 2018, like within this 10 months, we had no fraud at this card. So these are legitimate transactions from this cardholder. Now let's try to get into the mindset of the rule set and of the agent, right? Now we have the first transaction a couple of months later. Again, British Airways. The amount is rather high, but probably typical for this customer. I would say this is not fraud, if you agree. Next one. What do you think? We have a customer, this customer buying online tickets in Austria for a concert. The amount is 320 francs, probably appropriate for this type of transaction, rather low for this customer. What do you think? let's say, who says it's fraud? Right. It's not fraud, actually. But let's say, you block this transaction, you make him a bit angry. It's not a big story, right? Next one. A month later. Thomas Cook transaction. 1,600. I mean, I chose this merchant because they cannot hunt me, probably. Right? So the amount is typical for this customer. The currencies are typical. The country doesn't really make a difference because that's where the Thomas Cook merchant is located. If I would have seen that one, I would have said that this is not fraud. Who agrees? Right, okay. Who does not agree? Who thinks this is fraud? Okay. Next one. 45 minutes later. The exact same transaction. The same merchant, same currency, same country. Now, I guess it's clear this is fraud. And this also makes the previous transaction fraud. But we've already lost 1,600 Swiss francs. Right. Now, the problem we have here is we could say, okay, we have the exact same transaction. We can put a rule that does exactly that, rejects the second transaction that is exactly like the previous one. But this would be too naive, actually. This would just create a huge number of false positives. And this is what I wanted to show here. I mean, there are a few more transactions. The point I wanted to make is that it's very difficult to build rules that you give to a system to decide. It's sometimes even difficult for a human being to make the right decision. That's why you usually call the customer after an alert and you say, was it you or not? So the way issuers have modified their fraud prevention landscape is like that. So they either have a score within their risk engine, or they have the risk engine that produces alerts and blocks authorizations. And then what we do, for example, all approved authorizations go through our machine learning model, and we generate alerts that are being checked again by the fraud analysts. We'll focus here, as you would expect, just to give you an idea what we do. We heard very good ideas before in the presentation. We do very similar things. So we build individual profiles in 3 dimensions. The first dimension is the card. We calculate, for example, the average amount per authorization in the past week, past month, past year. We calculate the velocity. We calculate the number of days with at least one authorization during the month. So we're interested in finding out whether, if we have a customer with 30 transactions, whether these 30 transactions have been spread, one on each day of the month, or all 30 have been done on one day, because this is characteristic of the behavior of the customer. And then we have the second dimension, which is a card holder, who might have several cards. And there we try to understand what kind of transactions, which merchants this customer prefers, usually. And then we have a third dimension, very, very difficult or very, very interesting dimension. This is the merchant category or country dimension, where we also have fraud ratios. These are very, very interesting features to use in our models. So we calculate the number of legitimate or the number of fraudulent to the number of total authorizations in the past week, month, year, number of cards in the past month, number of distinct cards in the past month, and we feed them into our machine learning model, and we get a prediction. So in the previous case, the fraud model worked nicely, identified this first Thomas Cook transaction with a probability of 90%. The second one, 11%, the third one as well. Then the fraudster changed merchant, who gave a high score again, the first and the second transaction. Now the problem is, we have this system in place, and we have an agent looking at this number. They see that this transaction is kind of typical for this customer. They are doing travel transactions. They are used to spend that much money for tickets. They do it online. Should they trust this number? Should they block the transaction or the card and then annoy the customer, or let the card open and allow the fraudster commit more fraud? And this is where we focused our work in the past year almost now. And this is the main part of this presentation. It's interpretability. When we're talking about interpretability, I found this nice definition here. Interpretability is the degree to which a human can understand the cause of a decision, of a model decision in this case. Interpretability is important for several reasons. Of course, we have compliance and auditing. This is particularly relevant if you're doing credit risk, for example. But in all cases, even in fraud, where auditing is not the first priority, let's say, understanding of a model and improvement of a model can be achieved by understanding or interpreting single predictions, and of course, identification of algorithmic bias. This is, by the way, a very big point. There's a huge hype right now. If this is the first time that you hear about algorithmic bias, this is definitely not the last one. Human curiosity is the last point I mentioned here. Of course, when you expect that the transaction is non-fraudulent and you see that the model has given a high probability, you want to satisfy your curiosity. You want to understand why did the model give such a number. You have several choices when building machine learning models. One is to choose a model that is interpretable by nature. So we have here linear regression. We have this example from this book here. We try to predict the income of a person based on their educational level and their seniority. Let's say we have trained our model on a huge number of records, and we can identify or assign values to these weights, Vita0, Vita1, Vita2. And then we know if we have a new record coming in and we see an income of 100,000, then we know that it's because of these single weights that we assigned this value. A second model that is interpretable by nature is the decision tree. Here we have the Titanic dataset. Data scientists are aware or know this dataset. It contains information about all the passengers of the Titanic, along with a target variable survived or not. And the machine learning model is actually quite precise. Even a decision tree is quite good at telling us that if you are a male, 30 years old, with your 2 children and your wife, then you have a high probability that you survived. Third algorithm, k-nearest neighbors. Here the aim is to classify this square box. What we do here is we define a neighborhood of 3 points in this case, k is equal to 3. And then based on the color of the majority of the neighbors, we assign a color to the square here, in this case, light blue. This is also understandable. We understand that the color is light blue because the majority of the neighbors is light blue. The other possibility that we have is to use the so-called model-agnostic methods. Model-agnostic methods separates the explanations from the model itself. And this comes with several advantages, of course. The first one is we're flexible to choose model. We don't need to choose only the 3 models that I mentioned before. We can use random forest, gradient boosting, deep learning, whatever we want, at least in theory. Explanation flexibility is another advantage of these methods. So we can decide whether we want to explain a model on a high level, maybe by using the importance of the variables, as you've seen in the previous presentation, or you can even go down to the single prediction and understand why a single prediction has been given a certain score. Representation flexibility, here I mean that there are different algorithms. You can model your model by using weights or by using decision trees and so on and so forth. This comes, of course, at a cost. Most of these methods are computationally expensive, and some of those methods are, under certain circumstances, inconsistent. Here I list a few of the methods that we've been working with. Feature importance is a very typical method. The idea is to interpret the model as a whole, understand which variables are important for this model. Then we have a number of methods that allow us to understand the effect of a variable on a single prediction or in a model as a total. And then we have these three methods that allow us to do both model interpretation, but also single prediction interpretation. To the best of my knowledge, this last one, Shapley value explanations, is state of the art, or is considered state of the art right now, and this is the one that we've been using at Viseca. What are Shapley values? Shapley values is a method that comes from game theory. It's 70 years old, I think. So the idea, we have a problem. We have a group of differently skilled participants that are all cooperating for a reward. And now the question is, how should we split the reward in a fair way among the participants of this group? In a similar manner, for our models, we have a group of differently important features that are all cooperating to produce a score. And now the idea is to attribute or to split the score into the contributions of each of those features. I always found it difficult to understand this method. I found yesterday an interesting example online, and I adapted it for this case. Let's say we have three players, Michael, Scotty, and Dennis, playing a 3-on-3 game, basketball, for the fans. And we know that in this game, they all scored together 90 points as a team. We're also able to calculate the so-called characteristic function that tells us what would have happened if the team consisted of only part of these three guys. So in this case, we know that if Michael has played alone in the team, he would have scored 70 points. If he would have played together with Scotty, they would have scored 86. Dennis is probably weaker. Alone, he would have scored 56. Together with Michael, 82. So this is a bit the idea behind this characteristic function. It's also kind of easy to calculate something like that for our features by just dropping features when we calculate the different scores. And now the Shapley values work as follows. We create permutations of teams where we try to attribute to each player its value based on the order in which they were added to the team. This sounds complex. Let's try to make it a bit simpler. We have Michael. We know if he had played alone, he would have scored 80 points. Now we add a second person to the team, Scotty. We know that Michael and Scotty together would have scored 86 points. But 80 points have already been given to Michael, so Scotty gets only 6. If we add Dennis, we need to subtract 86 from 90. Dennis gets 4. Another example, we have Michael again. Now we add Scotty first. We know that Michael and we add Dennis first. We know that Michael and Dennis together would have scored 82 points, so we attribute 2 points to Dennis. Scotty then would take 8 points. If we change the order and we add Scotty first, then Scotty would take 70 points. Then we add Michael. Michael doesn't want to join the team as a second. Okay, here he is. So we have 86 points. We subtract 70, 16 for Michael. Then we add Dennis, 4. In the end, we continue this story, and then we see that if we average these values, we get the contribution of the players to the final score. So in principle, we have a team with a score of 90, and now we attribute 40 points to feature Michael, 30 points to feature Scotty, and 20 points to feature Dennis. This is a bit the idea about Shapley values. Now, we go back to our example. We have these 5 transactions we would like to have a look at and understand. The first one is the first Thomas Cook transaction for 1,600 francs. The currency is Hungarian forint, I think it's called in English. The first thing that we see here is this bias. This tells us what the model would have scored if no features were available, which tells us that, in principle, we tell that each transaction is non-fraudulent. And we will have it in all of our transactions. Now, the first interesting attribute that I see here is this ratio of the amount of the current transaction to the average amount at the same merchant during the past 13 months. You see that this has a positive impact. It goes into the direction of fraud, and it also tells us that 1,600 Swiss francs is a rather high amount for this customer at this merchant, if this customer has been at this merchant, or is a high amount in comparison to the imputed value that we use if we have missing values in this column, in this feature. Another feature is whether the transaction has been performed at using Swiss francs or another currency. And you see the fact that it's not Swiss francs has a positive impact in this case. So, direction fraud. Again, at a totally different case, you might have the exact same feature pointing downwards. Keep in mind, this one here, we will see it again. It points upwards here. Right? Here we have the same feature as before, this case with at this specific, or using this specific currency. So the amount of this transaction to the average amount using this currency in the past 13 months. And then this one is also the, how should I say, the distance, the relative distance between the amount that we have at this merchant now and the average at this merchant. So it's independent of the card, it's dependent only on the merchant. Let's go to the second transaction. So here, if you remember, we have 11%, 10.7%. And we want to understand why. The first thing that is interesting, in my view, is the fact that right now, this variable that we had before, that was pointing towards fraud, points in the other direction. Any guesses why? Sorry? This is correct, exactly. The day has changed. So at some point, we have to define what is past and what is present. And we chose for this specific model back then, we had as a inflection point, we had midnight. So in this case, all the transactions that took place before midnight are considered legitimate, which means that this customer has been now at this merchant and has actually done the exact same amount, and this transaction is considered legitimate. The same holds for this feature. Maybe just to mention, hour of day is rather atypical for this customer, so it goes in this direction towards fraud. Again, the third transaction, 1,300 Swiss francs. You see the contributions are again in the direction of non-fraud, and maybe I should quickly explain what this variable here is. It's a recency variable. It tells us when was the last transaction from this card when we build the training data set. And it seems that it's not uncommon for this customer to have a transaction at the previous day, whatever this day has been in the past. Now, the fraudster has decide to change merchant. And what we see here is that suddenly the ratio of the amount is to the average amount of this merchant is again high. The hour of day is atypical, especially if we combine it with the cardholder age. And last transaction, again, the ratio is rather high. You see, they even try much larger transactions right now. We have a variable here that tells us what is the ratio of the number of authorizations that were fraud to the total number of authorizations of this merchant. So rather high in this case. And the last point I would like to make is, regardless of the fact that this method is actually very useful if you understand the features, you might end up in a situation where the most important features, 20 in this case, allow you to reach a probability of something like 65%. And then all the rest of the maybe 100, 200 features contribute to this difference of 30% to arrive at this 95% probability. To start summing up, what we haven't covered here is everything that has to do with the algorithm selection and the training. We haven't discussed the performance of this model. We haven't discussed at all about the deployment and monitoring. You need a conference for that. For next year, maybe. And we haven't discussed about new or different directions that we are working on right now. One is the convergence of authentication and authorization in order to try to reduce the number of false positives on one side and the number of interactions with the customer on the other side. Deep learning, of course, huge hype. Graph algorithms, maybe graph algorithms with deep learning, definitely a possibility. To sum up, fraud prevention is very challenging, as you've seen in this example, not only for risk engine, but also for humans sometimes. But we believe that machine learning can help in these cases where it's difficult to differentiate between fraud and non-fraud. But these algorithms, usually the good ones, operate as black boxes. This has been mentioned in previous talks as well. So explaining these black boxes will make our models robust because we'll understand them and we'll be able to improve them. And what is very important is that it makes our fraud agents trust our models because they understand why a score has been given to a certain transaction and they can make a better decision. Finally, especially if you're interested in the topic of ethics or if you're doing credit risk or both, explainability is extremely important if you want to stay compliant and if you want your algorithms to be less biased. And with that, I would like to thank you for your attention.
Thank you. Thank you. Thank you so much, Viton. We have time for a few questions. Who has anything in mind?
In the last slides, you showed that there's a large increase in the rest.
Right.
So in the end, you have you end up not explaining why.
I mean, of course, you can plot another 100 features, right? And really see what of those 80 remaining features contributed to this 30% difference. My point, the point I want to make here is actually that in the end, even if this is called interpretable, you might end up in a situation where you have 500 features that contribute equally, let's say, to a final result. And in the end, we as humans cannot really interpret the interpretable result. Mm-hmm. I mean, you might have an attribution, but this doesn't make the result intuitive.
Okay, and those were Shapley values that you were showing?
Yes, 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 yes.
Thanks.
Anything else?
Yes, I have a question. You say make our company company compliant.
Right.
What do you mean by compliance?
I mean, depending on the country where where you are, I think in Switzerland, this is we are obliged to be able to give an explanation why we reject, for example, a credit application. You cannot say, my XGBoost model gave a probability of 90% that you will not pay back. You have to tell them, you know, it's your salary in combination with your age, in combination with the debt that you already have at this other bank that led us to reject an application. And now if you use XGBoost, which is a rather complex algorithm, in theory you can use such a method, or in practice even, and then you know exactly which features led to the rejection. And if there is a legal request to explain why an application has been rejected, then you can tell them these are the exact reasons. Of course, you have to be careful what kind of features you put in there. So if your model is racist by nature, then you have a problem if you're interpretable.
Yes, I have a second question because
Sure.
what you explained. Because I think it's very intrusive. You know by analyzing the behavior of your customer. I mean, you know more than the wife of this guy, for example. I mean, it's not going in data privacy regulation, personality. Are you compliant with this kind of regulation?
We're definitely compliant. I mean, you have to read what you sign. This one thing. You have the terms and conditions that allow us to use the data for purposes like fraud and risk. If you decide, for example, that you don't want to do marketing with us, in the European Union, exactly due to GPRS, how do you say it?
GDPR.
You say a mess already, even the GDPR, right? Sorry. Then the company is not allowed to use this data for marketing purposes, right? And this is clear. On the other hand, you have to trust as a customer that the company that you are selling in principle your data, or you're giving your data, depending on what kind of company this is treating your data properly. And Viseca is definitely one that treats them. I can say that I was surprised when I started how correct we are with our customers' data and the privacy of our customers. But it's not a given, I think. It's not a given.
Thank you.
The question about how you computed this individual contribution of the feature. I understood the Shapley, but then each individual contribution, how is it computed?
So in principle, what you do is, very good question. What you do is you have your features, let's say 100 features, and then you start adding them to a model, and then you calculate a score. And then you assign this score to the feature. Then you add the second feature, you have a new score, and then you assign the difference to the newly added feature. Third feature, so these are marginal contributions in a sense. The problem is,
so you do it for each prediction, you have to repeat the process.
Right. Very interesting point. This is correct. If you want to do it with some random algorithm, this might be computationally exhaustive.
Okay.
Right? But, and I don't know the details to be honest here, all three algorithms, ensemble algorithms, XGBoost in any case, comes pretty much, this calculation comes for free.
Okay.
I see. But the details.
So, but each time you have to retrain with that number of features
not
and
retrain,
have
rescore.
Yeah, rescore and have the additional delta.
Right.
Okay. I suppose you made only once for the ranking of features. You do every time for each prediction, which is different.
Yeah.
Okay.
This
Thank you.
This is the idea. Exactly. Thank you very much.
Thank you. Thank you again, Viton.
Thank you again.